we're now going to prove Theorem 12. All you'll be given in the exam is the theorem statement. So we're going to read that first. Let ABC be a triangle. If a line L parallel to BC cuts AB in the ratio S to T, then it will also cut AC in the same ratio. There's a structured approach to answering this question. We saw that in Theorem 11. And that is, you've got to draw a diagram. You've got to actually write down what's been given in the theorem statement. You've also got to state what you need to prove. You've got to do you have to adapt the diagram and comment on how you've adapted it. That's called construction. And then you go through the proof bit, which is the formal argument. So the first thing is, make sure we draw the diagram properly. So read the question again. It says triangle ABC, got it. There's a line L parallel to BC, got it. What's not on the diagram, but it's up here, is that the ratio of this section to the lower section is in the ratio of S parts to T parts. So that's what the diagram. So what have we been given? And indeed, that's what we write down. We've been given a triangle ABC, and the line L is parallel to BC, and this line L cuts AB in the ratio of S to T. What do we need to prove? Well, read the theorem. We need to prove that this line L cuts AC in the same ratio. So at this point, it's probably a good idea to label up these points. And we have to prove that the ratio of AY to YC is equal to S to T. Now, construction. Now, this is Theorem 12. And what we want to do is, if we can use Theorem 11 to prove Theorem 12, then our job is made an awful lot easier. And what do we know about theorem number 11? We know that a parallel line, in fact, we had 3 parallel lines, 1, 2, 3. And what we were told is each section between the parallel lines was equal length. So what we're doing now is we're expanding on that notion. We're doing a lot of parallel lines, and we're stating on this side that the length between each parallel line is identical. So, and what did Theorem 11 say to us? Well, if it's true of this transversal, it will also be true of the segments on this transversal. So we've end up with saying, we divide AX into S equal parts, and we divide XB into T equal parts. Through each point of division, draw a line parallel to BC. So this is what we've done. We've drawn parallel lines here, and we've written about it there. We've said how many sections are up here. There's S sections, because we were told that in the question, and how many sections are down here? T sections. Okay, so now we're going to embark on the proof. So what do we know from Theorem 11? Well, according to Theorem 11, the segments here must be the same length. Each of these segments must be the same length. So what we're going to do is we're going to state that the length of one segment is k, and we know that the length of each and every other segment on this line from Theorem 11 will also be of length k. Now, what does that mean? How does that help us? Well, we already know that there are S parts on this section and T parts on the section for Y to C. So we now know the total length. The total length of this section is S times K. And the total length of this section here, well, if each bit is worth K and there's T of them, then the total length of this section is TK. So we've now got AY is S lots of K and YC is T lots of K. mean, feel free to pause the video, go back over and think about what I've said. Line 4, well, what do we now know? Well, we're actually going to start the proof now. We're going to look at the ratio of AY to YC. Well, we know that AY is equal to S times K, and we know that YC is T times K. So we know that can be rewritten as this. We know this is a ratio, so we're allowed to divide across by the same number, and the number we're going to choose to divide across by is the common factor, which is K, leaving us with ST. So we've now proven that the ratio of AY to YC is in fact S to T. So all that leaves us to say now is that the proof follows.